And now it's action time! Let's design an ALU with a reduced instruction set. This module is our first complex design if we look at its functional specification. For this project, you are going to need the following Verilog files: alu.v and tbalu.v. Because the Verilog files have many lines, I've split the code in half for each file. The module has two 8-bit input ports for the operands, one 4-bit port for the operation, and one 8-bit output port and some flags. We will use a parameter to make the design adaptable to changes. If we look at the output ports, we already know how the code is going to look. The ones declared as output reg are going to be used in the left-hand side of always add blocks, and the ones declared as outputs are going to be used in continuous assignments. The flags are very easy to understand. We have the carry out that sets when we have overflow on addition. We have borrow that sets when we have underflow on subtraction. We have 0 that shows that y is 0, the parity flag, and a flag that shows that we have an invalid operation. This sets when we use an operation which is outside of the 9 declare operations. Since we are going to use many opcodes, we should declare some named constants and use those names instead of simple numbers in the design. It's easier to say now that we are executing operation decrement than operation 5. Another advantage is that if the code for operation has to be changed because of an architectural decision, we only have to update these codes rather than update the complete design. A local param is a Verilog constant similar with a parameter, but it cannot be changed from outside the module. This is a design technique used for constants that shouldn't be changeable at module instantiation. Our ALU does 9 operations and their description is very easy. We have a plus b plus carry, subtract b from a, increment a, decrement a, bitwise AND between a and b, not a, rotate left a, and rotate right a. At line 29, we start the combinational block for the ALU. Each time one of the signal from the right-hand side change, this block starts executing. At line 30, we have the default values that y and the flags get at the beginning. Next, we have a case centered around opcode. Now you can see how those local params come handy when we try to understand our code. Everything about this code shows simplicity. The operations are implemented exactly the same as we described them in the arithmetic operations table. Try to associate these operations with the ones from the table in the previous video. What's really interesting here, and is actually a pro tip, is at the upinc and updec codes. We used 1b1 instead of 1, so the synthesis program to use an 8-bit adder or subtractor, otherwise it would treat it as an integer operation on 32 bits. This happens only for some synthesis tools like Intel Quartus. At line 45, we calculate the parity. If the result y has an even number of 1s, then this flag will be 0, otherwise it will be 1. Parity bits are widely used in data transmission and in telecommunications. The testbench is as simple as it could be and is extremely similar with our previous testbenches. We first declare the testbench variables. We use reg for module inputs and wire for the module outputs. Next, we instantiate the DUT and connect the parameters and the ports. After this, we start monitoring the I/O ports and test the design with opcodes from 0 to 9. I want to make a disclaimer that this is not actual digital verification, it's only a simple stimulus generator that is not performing any checks. A true testbench with automatic verification will be done in one of our next chapters. After you run the testbench, you should get these results in the console. Feel free to add more combinations of operands in the testbench, recompile, and run again to see what happens. What do you think? Is our ALU working correctly? This is the synthesis results of our module using Quartus Prime Lite for a Cyclone V FPGA as a target device. Look at you, you're becoming a digital designer. Congratulations! You just designed your first synthesizable ALU using Verilog.